Good morning, everyone. I, Mr. Prasad Kalavajmat, Department of Mechanical Engineering, SG Bioconur Institute of Technology. Welcome you all for the third session. In the first session, we have covered the basic concepts of radiation, and we have taken up the emission characteristics of the surface, wherein which we have studied the black surface. What is a black surface? What is the emissive power, emissivity, and monochromatic emissive power, emissivity, and what is a gray surface, black body radiation, Planck's law, Wein's law, and Stefan Boltzmann's law. We have not only studied the emission characteristics of the surface, we have studied the radiation incident on a surface. We have understood what is total hemispherical irradiation, absorptivity of a surface, reflectivity of a surface, and transmittivity of a surface. So today, let us, once we have understood certain laws, let us solve a problem on those laws, and then we'll proceed further on this chapter. So the problem goes like this. Temperature of the sun's surface is 5779 Kelvin, and surface may be assumed to be black. Calculate the values of lambda m, EB lambda, where lambda is equal to lambda m, and EB on the sun's surface. Full stop. Also determine EB lambda, where lambda is equal to lambda m, and EB as received at Earth's surface. Full stop. Take mean distance between Sun and Earth to be 1.496 into 10 raised to 8 kilometers. Radius of the Sun is 0.695 into 10 raised to 6 kilometers. So to know the first value of lambda n, it is from the Wein's law. From Wein's law, I have lambda m is into T is equal to 0.00290 meter Kelvin. So lambda m is equal to 0.00290 divided by 5779 Kelvin. So this lambda m comes to around 0.5018 into 10 raised to minus 6 meter Kelvin, and most of the times lambda is measured in microns, so it is 0.5018 micrometer Kelvin. So I have from the Wein's law, I have lambda m into T is equal to 0.00290 meter Kelvin. I know the temperature of the sun at the sun's surface. It is 5779. So I get the maximum value of lambda m. Then I need to find out the monochromatic emissive power at lambda is equal to lambda m. That is, I need to find out EB lambda, where at lambda is equal to lambda m. This can be found out using Planck's law. From Planck's law, I have EB lambda at lambda is equal to lambda m. This is equal to 2 pi into C1 divided by lambda into I have exponential of C2 by lambda into T minus 1. So in our case, lambda is equal to lambda m. So this will be lambda m and this part also will be lambda m. I substitute the values. I know the constants. C1 is equal to 0.596 into 10 raised to minus 16 and C2 is equal to 0.014387. And I know what is lambda m. Lambda m is equal to 0.5018 into 10 raised to minus 6. And the temperature is 5779 Kelvin. So this is meter Kelvin. I substitute all the values in the Planck's equation. When we substitute the values, it will be 2 pi into 0.596 into 10 raised to minus 16 divided by 0.5018 into 10 raised to minus 6 into exponential of C2, it is 0.014387 divided by 0.00290 minus 1. Why I am taking it as 0.00290? Because according to my Wayne's law, lambda m into T is nothing but 0.00290. So we have here lambda m into T. Again, it's not necessary to substitute lambda m and T, which will be fetching me the same value, that is 0.00290 only. So I'm just substituting the same value here. This will be giving me a value of 0.83038 into 10 raised to 14. It is watt per meter cube. It is watt per meter cube. We have to convert this to micrometers. So it is 0.83038 into 10 raised to 8 into 10 watt per meter square micrometer. What I did, I have divided this equation by microns, that is 10 raised to minus 6. So we are deducting 10 raised to minus 6 from this 10 raised to 14. So for us, EB lambda at lambda is equal to lambda m at the sun surface is 0.83038 into 10 raised to 8 watt per meter square micrometer. Then I have to find out the maximum emissive power, that is EB. EB is given by Stefan-Boltzmann law. It is Stefan-Boltzmann law. According to my Stefan Boltzmann law, EB is equal to nothing but Stefan Boltzmann constant into the absolute temperature raised to 4. So this is nothing but 5.67 into 10 raised to minus 8 into 5779 raised to 4. So this EB comes to around 63.24 into 10 raised to 6 watt per meter square. So this is all about EB, and EB lambda is all about at the sun's surface. So I have a sun. It is emitting rays in all the directions. And let me consider Earth, which is at a distance from the sun's surface, which is at a distance of 1.496 kilometers, 496 into 10 raised to 8 kilometers. Then we have the radius of this sun. Radius of sun is around 0.695 into 10 raised to 6 kilometers. When we compare the radius of the sun to the radius of the earth, it is negligible. So we are going to consider only the distance from the sun's surface to the earth's surface. So for me, this is the sun and this is the, and again we are going to find out EB lambda at the earth's surface as well as EB at the earth's surface. So I know the distance from the sun to the earth, it is 1.496 into 10 raised to 8 kilometers, and radius of the earth sun is 0.695 into 10 raised to 6 kilometers. The radiant heat flux coming out of the sun will always be the inversely proportional. It will always be inversely proportional to the square of the distance from the sun. So, so EB lambda EB lambda at lambda is equal to lambda m. It will be nothing but the EB lambda at the Earth's sun's surface, at sun surface, multiplied by inversely proportional to the distance. That is the radius. It is 0.695 into 10 raised to 6 to the distance of the sun to the earth. It is 1.496 into 10 raised to 8 square. So EB lambda at the sun's surface is 0.83038 into 10 raised to 8 into 0.695 into 10 raised to 6 divided by 1.496 into 10 raised to 8 square. So this comes around at the Earth's surface, it comes around 1792 watt per meter square micrometer. So EB lambda at Earth's surface is 1792 watt per meter square micrometers. Along with that, I need to find out EB at Earth's surface. This will be also EB at Sun surface multiplied by the square of the distances. It is 0.695 into 10 raised to 6 divided by 1.496 into 10 raised to 8 square. So EB at the Sun surface is 63.24 into 10 raised to 6 into, we have whatever is there in the bracket, 0.695 into 10 raised to 6 divided by 1.496 into 10 raised to 8 whole square. So this comes around 1365 watt per meter square. This is a value which is also called as a solar constant. It is also called as a solar constant at the Earth's surface. So this is all about the problem number 1. Let's go to the problem number 2. I'll just give you 2 minutes to read. The problem goes like this. Variation of a monochromatic irradiation, that is H lambda, on an opaque surface and the monochromatic absorptivity alpha lambda with lambda is shown as shown. We have a graph which is shown with alpha lambda. We have a graph which is shown with alpha lambda, that is absorptivity, monochromatic hemispherical absorptivity, and H lambda, that is monochromatic irradiation. Along with the x-axis, it is varying along with the wavelength, that is lambda, and wavelength is varying from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and in both the cases. And in between 2 to 8, in between 2 to 8 for the wavelength, in between 2 to 8 for the wavelength, we have H lambda is equal to 750 watt per meter square micrometer. H lambda in between the wavelength 2 to 8, we have 750 watt per meter square micrometer. And alpha lambda in between 0 to 4. Alpha lambda in between 0 to 4, we have 1. The value of alpha lambda in between 0 to 4, it is 1. And from 4 to 8 alpha lambda, this is the curve, its value is 0.5. I repeat, we have in the first sentence, it is given that the variation of monochromatic irradiation on an opaque surface and monochromatic absorptivity with lambda, that is the wavelength, is as shown. So these are the two graphs which is shown. To read the graph, on my x-axis we have the wavelength, and on the y-axis one is So monochromatic irradiation. The other one is monochromatic absorptivity. This monochromatic absorptivity, it is varying from 0 to 4. It is varying with the value of 1, and from 4 to 8 it is varying with the value of 8, 0.5. And this H lambda, that is monochromatic irradiation, in between 2 to 8 it is varying with the value of, it is having a value of 750. So once I know what it is varying, what I have to calculate is, first one, absorbed radiant flux, that is HA. Second one, absorptivity. And the third one is reflectivity. So I have to find out absorbed radiant heat flux HA and absorptivity and reflectivity. From the characteristics of radiant heat flux falling on a surface, we have studied, we'll go to the solution. We know that the absorbed radiant heat flux, which when varied along the wavelength, gives me HA lambda into D lambda. And according to the monochromatic hemispherical absorptivity, alpha lambda will be equal to HA lambda. Alpha lambda will be equal to HA lambda divided by H lambda. So HA lambda is equal to H lambda into alpha lambda. So I substitute the value in this equation. It is 0 to infinity. It is alpha lambda into H lambda into D lambda. So now I have 0 to infinity, but for me the graphs are varying from 0 to 2, 2 to 4, 4 to 6, 4 to 6 to 8. So we have some values of alpha lambda. Alpha lambda is varying between distances for different, from 0 to 4 we have 1 and 4 to 8 we have 0.5. So I'll split this integration. This integration I'll take it from 0 to 2, 0 to 2, alpha lambda H lambda into D lambda, plus then 2 to 4, it is again alpha lambda H lambda D lambda, plus then we have 2 to 4, and 4 to 8 I have the same value. From 4 to 8, let it be in this equation and let it be in this figure. 4 to 8 we have the same value. So 4 to 8, it is alpha lambda H lambda into D lambda, plus it is from 8 to infinity. It is again alpha lambda H lambda D lambda. I repeat, I have 0 to infinity alpha lambda H lambda D lambda. Since we have different wavelengths here as shown in the graph, 0 to 2 I have different H lambda value. So I am going to convert 0 to 2 here. 0 to 2, 2 to 4, and 4 to 8, 4 to 8 in this case, and in this case we have the same value. So I'm changing the limits from 0 to 2, 2 to 4, 4 to 8, and 8 to infinity. When we see the value of H lambda in between 0 to 2, H lambda in between 0 to 2, H lambda in between 0 to 2, I don't have any value, it is a 0. So h lambda in between 0 to 2, it is 0. So this part will be equal to 0. Also, for me, h lambda after 8, h lambda after 8 is 0. H lambda after 8 is 0. So for me, this value after 8, it will be equal to 0. So what I'm left with is the second part and the third part. So the second part is what we are having. It is, this is HA is equal to, HA is equal to, we are having 2 to 4 alpha lambda H lambda into D lambda plus 4 to 8 alpha lambda H lambda into D lambda. Alpha lambda in this case, it is a constant, so I take it outside. Alpha lambda and H lambda is also constant, it is outside. In between 2 to 4 D lambda plus again alpha lambda and H lambda. In between 8 to 4, it is D lambda. So I'm having here, I integrate and I substitute the values alpha lambda, H lambda, 2 to 4 it is lambda, 4 to 2 plus I have alpha lambda, H lambda into I have the value of lambda in between, sorry, it is 4 to 8, right? It is 4 to 8, so it is 8 and 4. When I substitute the values, it is alpha lambda, H lambda, 4 minus 2, the limit it is 2, plus this is alpha lambda, H lambda, it is 8 minus 4, the value is 4. Now, alpha lambda in between 2 to 4, alpha lambda in between 2 to 4, the value is 1. Alpha lambda in between 2 to 4, the value is 1. And H lambda in between 2 to 4 is also 750. So alpha lambda in between 2 to 4 was 1 into 750 into 2 plus alpha lambda in between 4 to 8, alpha lambda in between 4 to 8, I had a value of 0.5. In between 4 to 8, we have a value of 0.5. So alpha lambda in between 4 to 8, it is 0.5 into 750 into 4. This comes to around 3000. This comes to around 3000 watt per meter square. That is absorbed radiant heat flux. Now, absorptivity alpha is nothing but, for us, the total radiant absorbed heat flux HA divided by H lambda over the wavelength. H lambda over the wavelength. So it is 750 into 6. It is nothing but from 2 to 8, it is, its value is 750. Rest all it is 0. So in between 8 minus 2, it is in between these 6 wavelengths. The value of H lambda is nothing but 750. So it is 750 into 6. So this is HA is 3000 divided by 750 into 6. This comes to around 0.667. And also we know that the surface is opaque. We have an opaque surface. That means transmittivity will be equal to 0. So alpha plus rho plus tau is equal to 1, tau is equal to 0, alpha plus rho is equal to 1. So I have to find out rho, that is reflectivity. It is 1 minus alpha. So alpha is 0.667 from the above equation. So rho will be nothing but 0.333. So the reflectivity for this equation will be 0.333. This is all about the problems what we have solved today. Two problems. In the next class, we will start with the solid angle and radiation intensity. These are the two problems what we have solved today. If you have any doubts, you can just ask me.